So good morning to anyone who is in my part of the world, and good afternoon to those of you in Russia and elsewhere in Europe. Good evening to anybody who's joining from Asia. It is a strange experience for me to be giving this class from my home office in the basement of my house in Rochester, New York. But we'll give it a try here and see how it goes. I had a wonderful time doing this, the same school last summer in St. Petersburg, and I was really looking forward to being in Moscow right now, but I'm sure I will have another chance at some point to get there. Can we switch over to the slides? Excellent, thank you. So for anyone who doesn't know, Rochester is a city in state in the United States, in North America. It's a city of about 1 million people. The University of Rochester is a small private research university with just under 12,000 students. It's on the Genesee River in Western New York State. And if you're familiar with a map of North America and you know where the Great Lakes are, Lake Ontario is easternmost lakes, and we're the middle of the south shore of Lake Ontario. The nearest world-class city is Toronto. It's about a 3-hour drive away. New York is about a 6-hour drive. I don't get there very often. Here's an aerial view of the campus. The academic buildings in the foreground and the Genesee River going around the bend. You can see the river flowing toward downtown in the background, and Lake Ontario is at the horizon. The computer science department, where I teach and have taught since 1985, was founded about a decade before my arrival in 1974. We currently have about 20 tenure track faculty and about 70 PhD students, lots of master's and bachelor students as well. We're particularly well known for work in artificial intelligence and in parallel and distributed systems, with several other specialties as well. In this class today, I'm going to be assuming that everybody has some familiarity with multi-threaded programming, ideally in C or C++, but Java or any other concurrent language would be okay. And hopefully most people who are listening in know at least something about non-blocking data structures and synchronization techniques, although I'll be trying to fill in the background that's needed there when we get to it. We have a total of 3 hours today, divided into 2 halves with about a half an hour of a break in the middle. In those 3 hours, I'm going to try to survey the high points of material I devoted an entire class to this past semester. So we obviously won't be able to cover everything. My emphasis is going to be on cross-cutting issues and techniques, things that are generalizable to lots of different situations. You'll be able to look up the details of individual data structures and performance results, theorems in the papers. And I'll try to cite specific papers as I go along so you'll know where to look. I've told Dmitry and Nikita, who are watching the chat in Telegram, that if anything I'm saying is unclear, please feel free to interrupt me with questions. I would much rather answer a question than continue to be confusing. I'll also stop at several points during the talk and invite questions, just because it's kind of a natural break. If you're interested in more background on concurrent programming, you might check out the Morgan and Claypool monograph that I published about 7 years ago. There's several chapters of this, 3 and 8 in particular, relevant to today's talk. Most university libraries have a subscription to the Morgan and Claypool series, so you can get it online there. As an undergraduate in the late 1970s, I made heavy use of a couple of the last machines that had magnetic core memory, a PDP 1170 and a UNIVAC 1108. This was memory that, as shown in the picture in the upper right of this slide, had tiny little magnetic donut-shaped or torus elements that could be magnetized in either direction, and they were strung on wires with 3 wires through each to set and reset and sense the magnetic fields of the little cores. This is why we still talk today about a core dump. A core dump is a post-crash record of the contents of the magnetic cores of the 1960s or 70s computer. But by the end of the 1970s, magnetic core had been replaced by dynamic RAM in almost all situations, and RAM has ruled since then. Over about a 45-year period, we have seen 7 orders of magnitude increase in the density of dynamic RAM, from about a kilobyte per chip in 1970 to as much as 16 gigabits on a chip in 2008, and you can get 64 gigabytes on a DIMM module to plug into your computer. But DRAM is basically at the end of its life. We don't expect to see any significant increases in density going forward, and it's because you can't shrink the capacitors that hold bits in DRAM anymore. If we make them smaller, then they leak too fast and background radiation can flip the bits. So we are basically at the end of the road for DRAM. It's also power hungry. Because of the leakage, DRAM requires refresh at about a kilohertz rate. Once every millisecond, we've got to write the value of DRAM back into the cells. And in a typical data center today, refresh of DRAM consumes about 25% of the total energy budget. There are multiple technologies under development or now commercially available to replace DRAM. They're all being developed in order to provide higher density and lower energy consumption. But it turns out that the main way you get higher density and lower energy consumption is by using techniques that happen to be non-volatile. That is, they keep their content when the power is turned off, just as magnetic core did back in the 1960s and 70s. Now, we could choose to just use this new, dense, cheap memory the same way we've always used DRAM. We make a distinction between the working memory that your program has while it's running and the persistent storage that you use to hold information after your program has finished. That distinction may simply be a good idea. And 10 years from now, we may look back and say, everything I'm talking about today turned out to be irrelevant, and we just want to use non-volatile memory the same way we use DRAM. That's possible, and I'm not going to make an absolute prediction about it, but my hope is that we will be able to leverage the non-volatility of these new kinds of memory to do exciting new things, to basically rethink the entire storage hierarchy so that we can keep data in-memory format across program runs and even across system crashes. And this class is devoted to exploring this second option. So I want to talk a little bit today about non-volatile memory technology and about the hardware architectures into which we insert it. I want to talk some about the challenges of keeping information in non-volatile memory over long periods of time, and talk about correctness criteria for software that's designed to do so. I think that will take us up to kind of a natural break for the half hour in the middle of this class, and then in the second half, I want to come and look more closely at particular persistent data structures, at runtime systems designed to generalize across many persistent data structures, at the specific problem of memory allocation, which turns out to be surprisingly tricky, and a brief mention of several other issues, including an advertisement for my talk at Hydra tomorrow. So let's start with non-volatile memory technology and hardware architecture. There are multiple kinds of non-volatile memory under development or currently available, and I'm not a hardware expert, so I can't answer detailed questions about how these work, but it's important for a software person like me to at least understand the characteristics of the technology so that you know what the implications are for software. Many of you will have heard of Intel's Optane memory, which is now commercially available. It's an example of phase change memory. It's essentially a microscopic analog of the same technology that was used in rewritable compact disks. It's crystalline chalcogenide compounds. Chalcogenides are sulfides, selenides, tellurides. They're semiconductors that can be melted and then allowed to solidify quickly or slowly. If they solidify quickly, they produce an amorphous solid. If they solidify slowly, comparatively slowly, they produce crystalline solid. And those two solids have different resistances, and that's how you sense the value. Amorphous will be either a 0 or 1, and crystalline will be the other, and you run electric current through, and you can tell by the resistance whether it was cooled slowly or quickly. And the slowly or quickly is fewer or more picoseconds. It's very fast, but different at that granularity. There are other technologies under development, though. So Hewlett-Packard has, for instance, made a lot of exciting public announcements about resistive RAM technology, which they call memristors. These use ion migration in a metal oxide layer on your chip in order to grow or to destroy conductive filaments that can connect layers above and below. And again, you measure resistance. By applying voltage across the metal oxide, you can grow or destroy these conductive filaments. Then there's spin transfer torque magnetic memory, or ETMRAM. This is now available from TMS as part of their standard processes. So if you want to design a chip that has STT-MRAM on it, TMSC will manufacture it for you. This uses a quantum effect. It has two layers, one of which has the electron spin of its electrons kind of frozen in place, and the other of which is permeable. And you can either align the permeable layer with the electron spin of the fixed layer, or you can break it so that the spins are chaotic. And again, you sense the difference with resistance. One of the nice things about STT-MRAM is that it's compatible with CMOS process technologies and can be used on chips along with logic. And finally, there's ferromagnetic RAM, which has been around a long time. It's very similar to DRAM, but instead of using capacitors, it uses tiny little magnets on the chip. It has roughly the speed and density and cost of DRAM, slightly poorer than DRAM on all of those accounts. It's widely used in tiny embedded devices where non-volatility is important, but people don't really expect it to be a mainstream technology for memory in laptops and phones and servers going forward. Mostly these other three technologies, the phase change memory, resistive RAM, and STT-MRAM, are the ones that we expect to be seeing in the next few years. And I'm going to focus mostly on phase change memory, or Optane, in this talk because it's the one that's commercially available now in server class machines, and which I have on machines in my lab and can report results for. This is a table that gives you a rough idea of some of the physical characteristics of these different technologies. This table is a few years old, maybe 3 years old now. It was put together before Optane came on the market. So some of the numbers are a little bit off, but I chose not to try to update it because, again, I'm not really an expert on the technology. I would point out a few particular things in this table. Phase change memory, or Optane, which is the second of the columns of information here, is actually a little bit denser than is suggested by this table. At the moment, PCM is about 8x denser than DRAM in Intel's chips, which means you can get 512 gigabytes on one inline memory module, where the maximum you can get with DRAM currently is about 64 gigabyte. The read latency of Optane is about 3x higher than DRAM. So it takes 3 times as long to read if you're reading one location. Write time is about 10 times as long. So it takes longer to write it than it does to read it. The bandwidth is roughly comparable to DRAM, slightly poorer than DRAM, but not much. So right now, Optane is a great technology for building main memory out of if you're willing to accept slightly lower performance in return for lower cost and higher volume. And STT-MRAM is a potentially appealing technology for caches. It's much slower than SRAM, but it's denser, so signals have to travel less distance, and those balance out to a certain extent. I would also point out on this chart that endurance, or the number of times that you can write the memory before it wears out, is new for PCM, and we'll be coming back to that a little bit later in the presentation. So we should think a little bit about where non-volatile memory gets attached in the computing system. It could be just an alternative over on the PCIe bus to things like solid state drives made of flash or hard disks made out of spinning magnetic material. And Intel will actually sell you a solid state drive made from PCM, which is basically a high performance SSD, and you can attach it to the PCIe bus. But over on the memory interconnect, you can also attach PCM the same way you would attach main memory modules made out of DRAM, and that which I have circled in this picture is what I'm going to focus on in the talk today. And as I mentioned a moment ago, in the caches, you might use STT-MRAM in order to create non-volatile caches, but most machines are not envisioning that in the near future. For now, we can assume that the caches remain volatile. They lose their contents when the power goes off, but Optane memory here in the magenta circle will keep its value when the power goes off. So assuming we have attached the non-volatile memory to the memory interconnect here, we can think about how to use it. And Intel machines currently come with two hardware options that can be configured at boot time. One option is called memory mode. And in memory mode, the DRAM of the system works as a cache for the non-volatile memory. So for instance, I have a machine in my lab right now that has 192 gigabytes of DRAM and 1.5 terabytes of Optane. And if we boot the machine in memory mode, the hardware transparently gives me the appearance of a little more than 1.5 terabytes of memory and most of the performance of DRAM, because the DRAM is used as a cache for the PCM. And that's not visible to the programmer at all once you've booted the machine in memory mode. That means, of course, that your software can't use the Optane memory in any special way. It has to just continue to use transient memory for all of its operating purposes until the program ends. Alternatively, you can boot the machine in so-called app direct mode. And if you boot in app direct mode, then the non-volatile memory is directly visible to software and can be managed by the operating system. And the hardware does not attempt to use the DRAM as a cache for the non-volatile memory. Instead, some of the physical addresses in your memory space are DRAM, and some of the physical addresses in your memory space are non-volatile memory, and the operating system manages it. In Linux today, that management is done through something called direct access, or DAX mode. DAX mode, the non-volatile memory, which occupies certain physical addresses in memory space, is presented to applications as an in-memory file system. So you have a file system whose volume is your non-volatile memory, and files that are allocated in that file system reside in non-volatile memory. And then the operating system lets you mmap the file, add it to the address space of a running application, and when the application performs loads and stores to the mmapped file, it's not accessing a DRAM buffer for the file the way you usually are with mmap. Instead, you are directly accessing the non-volatile memory. So in DAX mode, you mmap a special file in this special file system, and then loads and stores to that special file go directly to the non-volatile memory. Of course, they still use the hardware caches, orange blocks in my picture here. But there's no intervening buffer cache in the operating system the way there usually is for an M-mapped file. Now let's say that we have a DAX image of non-volatile memory managed by the operating system and made available to programs. Now we can ask, how is our software running on top of the operating system going to use this special memory? One option, of course, is just to treat it as extra, very large, kind of slow memory. And that's attractive because it's 1/8 the cost of DRAM at present. For less than $5,000 US per terabyte, you can buy Optane now, and that's dramatically less than DRAM costs. You could also choose in software to manage the DRAM as a cache for the non-volatile memory, and there's a number of projects around where people have design software that uses the virtual memory system to put some pages that are hot pages in DRAM and put some pages in non-volatile memory. Notice this is different from booting your machine in Intel's memory mode, because now I'm talking about system software using virtual memory to choose what to put in which kind of page, rather than the hardware doing the caching behind the scenes. Third option is to use the non-volatile memory as a tool to optimize file systems and databases. So you could put hot relations or hot files of your file system into the non-volatile memory where they would be fed at than they are in flash or on the hard disk. Or you can put your indices for files and databases in non-volatile memory and hide all of this behind the usual file system or SQL interface so that application programs don't have to be rewritten. And then the final option with the star here on my graph, the one that I want to focus on today, is having application level software explicitly manage the persistent memory as a new abstraction, as memory that keeps its value across program runs and even across system crashes. So let's switch to that and talk about the challenges of using non-volatile memory explicitly in user-level programs. The first major problem is that caches are not directly controlled by software, and caches choose to write back their contents at arbitrary times. So if I perform several writes in my program, depending on the write-back strategy of the cache and the access pattern of my program, the caches may write their contents back to memory in a different order from the order in which I wrote them in my program. And that difference between program order that's visible above the caches and write-back order that's visible under the caches becomes an enormous problem in the event of a crash. Unless we do something special, main memory after a crash may not reflect a consistent cut of the happens before accesses of the application prior to the crash. So here's an example, very simple example with one thread. Suppose my thread allocates a node and initializes it to be used in some linked data structure. After the initialization, it sets a pointer to point at this new node. And then the system crashes. But let's say that before the crash, the cache wrote back the pointer. So my second line of code here gets persisted, but the cache hung on to the actual contents of the node. The cache lines that held the data of the node are still dirty in the cache when the crash happens. Now, if I wake my system up after the crash, I have this pointer that points at memory that never got written back. And so I have an inconsistent state here. I have a data structure that appears to be linked, but it's linked to contents that never actually got saved. The lesson to be learned from this is that if you do two things in your program, A and B, and if B depends on A, you have to explicitly persist A, that is, force the cache to write it back to memory and fence it so that you won't perform anything else until the original persist has happened. Intel machines provide mechanisms to facilitate this. In particular, there are 4 instructions in the modern Intel instruction set that are essential to low-level system software working with persistent memory. There are 3 kinds of write-back. There's the cache line flush instruction, which has actually been in the instruction set for a long time. It evicts a line from the cache system wherever it is and waits for it to reach memory. So if I issue a cache line flush on core 1 and I've never touched the line I specify in that instruction, but some other core has touched it and has a dirty copy in another cache, maybe even on another socket of my machine, the CL flush instruction will force that other copy into memory and will not allow me to proceed until the flush has happened. The waiting for the flush can take a long time. And so in recent Intel machines, there's a CL flush opt instruction, which has OPT on the end for optimized. That evicts the line the same way CL flush does, but does not wait for it. There's no implicit fence in the CL flush opt. This is particularly nice if you're writing back a whole sequence of lines. You can do a CL flush opt on line 1, line 2, line 3, line 4, and after you've written back an entire object, you do one fence. The write backs will pipeline. The last fence will wait for all of them to complete. And then there's one more instruction, the CLWB, or cache line write back instruction, does not necessarily evict the line. The idea is that it should allow you to keep a shared copy of the line in your cache in case you plan to keep using it. On current Intel machines, CLWB is just an alias for CL flush opt. It actually does evict the line, but the expectation is that future Intel machines will provide a CLWB that keeps the line in shared state. And then finally, the S-fence instruction, which again has been in the instruction set for a long time, will wait for previous write-backs that have been issued by this hardware thread. So if core 1 performs a write-back and core 2 does a fence, the fence does not wait for the write-back on core 1. It has no way of knowing about it. The fence is only for write-backs that were initiated by this issuing thread. So none of these instructions are cheap. Measurements suggest that they take a little bit under 100 nanoseconds each, but crucially, the write-backs, the CL flush opt and the CLWB will pipeline so that incrementally they take more like 5 nanoseconds each, and then the final fence takes the 100 nanoseconds. Once upon a time, 2 generations back, a CL flush took hundreds of cycles, and that was because it had to wait for the flushed line to get all the way to the DIMM across the memory interconnect. On recent Intel machines, the memory controller on chip has a large capacitor in it, and the hardware promises that anything that has been acknowledged by the on-chip memory controller will make it all the way to memory on a power failure. The capacitor provides enough energy to flush the contents of the memory controller to main memory on a power failure. That means that the fence after a write back on a modern Intel machine, this is Skylake and later, takes only about 100 nanoseconds, not several hundred. But 100 nanoseconds is still a long time, and that means if we want good performance from persistent algorithms, we can't be too cavalier about our flushes and fences. We have to be very careful to issue them as few of them as possible in order to minimize the amount of time we spend waiting for them to finish. So before I move on to the second major challenge of working with non-volatile memory, let me point out that problems arise not only when one thread writes multiple things and needs to have them persist in the same order they were written. That was our first example. But it also matters when you have multiple threads active. So take a look at this example here. We've got one thread, thread 1, that allocates a new node and then writes it back and fences it. So I'm assuming that there's some sort of persist operation. It might be a library call, or maybe even something in your programming language that says, make sure this has been written back and fenced. And then it points something at it. That's what it was supposed to do according to our previous example. And after it updates the pointer, it's going to persist the pointer. So create the node, write it back and fence it, point something at it, write the pointer back and fence it. But notice that as soon as you change the pointer, the update to the data structure is visible to other threads. So consider this other thread, T2 over here. It wants to add to the list that we're building. It allocates the new, it persists the new node the way it's supposed to. And then it tries to update the next pointer of the node that was created by thread 1 and does so. But now suppose we crash. And in the crash, the new node from T1 has been persisted, the new node from T2 has been persisted, and the pointer down here has been persisted, but the original pointer up here, sorry, the pointer in thread 1 has not yet been persisted because thread 2 saw what thread 1 did before thread 1's core had finished persisting. Now on a crash, we may have a pointer that did not get written back. So this dotted line indicates that this pointer did not manage to persist before the crash, even though these other objects did. So we've leaked memory. We allocated and thought we had linked in memory, but the pointer to it did not get persisted before the crash. The lesson to be learned from this example is that writing back your updates is not enough. You also have to make sure that when you read something that you depend on, the thing you read has been written back, even if the thread that created it hasn't had a chance to write it back yet. So generally, you have to help threads that update things that you depend on. If you read them, you persist them just in case the other thread perhaps got preempted between creating the thing you saw and persisting it. This is probably a good place to pause for questions. I've noticed my phone vibrating a couple of times. Dimitri or Nikita, are there questions that we ought to handle right now? I'm not seeing any, so I'll keep going. Okay.
I don't.
Second major problem. Whoop.
Yeah, now we see each other, but we don't see the slides. Can we see both everybody in the slides? Super. Could you please come back to the previous slide with the code?
No.
Yes. Thank you. And here you need to persist the memory. You need to persist your updates. And I don't understand whether the memory can be persisted just eventually. So what guarantees do you have? Is it possible that without this persist instruction, you still, after the crash, you can see that some memory is persistent and some is not?
Yeah, the memory works in the normal way during crash-free operation. So eventually caches write everything back. When your program exits and other programs make use of the memory, they'll force what you did out of the cache and everything will be fine. The problem is that a crash may occur when some things have been written back from the cache and some things have not been written back from the cache. And then if you wake up and try to use what's in memory, you may discover it's inconsistent. The key point in this particular example here is that there is nothing T1 can do to prevent the problem. T1 has created a new node and forced it to be written back to memory. It's initialized a pointer to reference the new node, about to force the pointer to be written back to memory, but maybe it gets preempted right here between initializing the pointer and persisting, which is why I wrote persisting in light gray. And now thread 2 sees the pointer. The pointer may be an atomic variable in C++, so this could be a data race-free program where T2 has been waiting for the pointer to be initialized, and as soon as it sees it, it goes ahead and it adds more node to our list. Now, the possibility that we'll crash before T1 has had a chance to force the cache to write back this pointer. And then we'll have leaked memory. We'll have allocated memory where allocated memory that's unreachable after a crash. And this is only one example of a cross-thread problem where one thread makes a change and a second thread sees the change and acts on it before the first thread had a chance to force it into persistence. And that's why we have this general rule that when you read something that you depend on, you have to make sure that that thing you read has reached main memory.
And so it can't reach the main memory until we persist it, right?
Oh, it may. It may get written back. Caches will things back when they need this, but you don't know for sure that they will. And you have to know for sure if you want to have consistency after a crash.
Yes, I understand this, but I'm just thinking about whether it is possible to have a problem because so I do understand that when we invoke persist, it's guaranteed that it is persisted, but probably if we if the memory is naturally persisted because of the cache coherence protocol, then after the crash we can see that some memory is persisted, some is not, and we didn't expect this. Oh, I see, and that's why we need to persist it when you did it, right? So when we did it, we need to be sure.
Right. If we read it, then we happen after the update that created it, which means if what we do is going to persist, we have to make sure that what we read has also persisted, or else memory will be inconsistent.
Isn't it expensive to persist memory after each read?
In general, yes. If you incrementally write back and fence everything, then you will be spending, 30 to 50 cycles for every write instruction, which is too much. And a lot of this class is going to be about how to avoid that. So let me move on to the second question, or the second problem. The first one was the need to control the order in which things are written back. The second problem is failure atomicity. So people who are familiar with the so-called acid properties of databases, atomicity, consistency, isolation, and durability, this is the atomicity and durability part. If I perform update to a data structure or a file system or a database, I'm generally interested in performing a complicated high-level update. I want to add something to a hash table. I want to rebalance a search tree. I want to update 6 fields of an employee record. And I want that entire change to be persisted or none of it. And that's a challenge. If parts of my update get written back to main memory, but the rest of it doesn't, then after a crash, I'll have an inconsistent partial update. So we need to think about the atomicity of complex high-level operations. So Generally, we think of a concurrent data structure as having operations that transition it from one consistent state to another consistent state, perhaps under the control of locks, perhaps in a non-blocking fashion. But if we're in the middle of an operation when a crash happens, we need to think about how to recover consistency after the crash. Very similar to problems we get in file systems and databases. Most people who are listening here are probably familiar with journaling file systems. Most modern file systems do journaling. So if I create a file, for instance, I have to update the blocks of the file itself and the directory in which it resides. And I want to do both of those or neither of them. And if my machine crashes halfway through the file system update, I want to make sure that I roll the whole thing forward or back. That's usually solved with some sort of logging, and I will be talking about logs a little bit more as we go forward. And then there are several other issues that I'm not going to be spending much time on today, but I want to mention them. One is read-write asymmetry. Optane and several other non-volatile technologies read more quickly than they write. So it may be desirable to design algorithms and data structures that do extra reads in order to avoid writes. PCM and several other kinds of non-volatile memory also have a wear-out problem. Almost everybody knows about this for Flash. Flash can be written maybe 10,000 times, and then it wears out. And most people are familiar with having a flash drive that isn't really usable anymore, or that has smaller capacity than it used to because the wear leveling software inside has discovered that some of the cells have failed. Well, PCM is a lot more durable than flash. It's about 100,000 times more durable than flash, which is great, but it's still 10 million times less durable than DRAM. So if we're going to be writing something a lot, we probably don't want it in PCM, we probably want it in DRAM. And we may need to think about software that does wear leveling and that uses DRAM for caching of hot objects, not just for performance, but also to reduce the number of writes. And we may want to think about designing data structures that minimize the number of writes in order to extend the lifetime of the memory. A third problem I'm not planning to talk about is full system recovery. I'm focused here on data structures that can be recovered after a crash and that are going to be consistent so you can keep using the data structure, but the applications that were actively using the data structure when the crash happened are gone. You could think about trying to design full system recovery so that on a crash, you would be able to restart the processes that were running when the crash happened and put their program counters right where they were at the time of the crash, make sure their stack contents is all consistent, and execute forward. I'm not trying to do that. I'm simply trying to make sure that particular deliberately specified data structures, things that we would traditionally put in a file, but now are putting in memory, are guaranteed to be reusable by new programs after the crash. And then finally, there's the issue of security. Most of us encrypt the disks on our machines because we're worried that if someone steals the top and takes the disk out, they can read it. If we encrypt it, they can't. This is a concern for non-volatile memory as well. If someone steals your laptop and can take the Optane out and look at the contents of the Optane unless it's encrypted. Encrypting on reads and writes file is fairly easy and can be done in software. Encrypting on loads and stores of individual cache lines is not something I generally want to do in software, and Intel has built it into the hardware of their machines. So the contents of Optane is automatically kept encrypted on Intel machines using a mechanism that I'm not planning to talk about today. So for this class, we need to figure out what it means for a persistent data structure to be correct. What is it exactly that we want to guarantee about the data structure after a crash? What do we have to fence and write back? When do we have to fence it and write it back in order to ensure consistency after a crash? And how do we know that we got it right? Maybe doing some non-trivial work during recovery, maybe not. We'll see both options later. And then given a clear notion of what it means to be correct, we want to know how can we get performance? What can we do to maintain correctness while minimizing costs? Which gets back to a question we had a few minutes ago about the expense of doing write back and fence instructions. Basically, how do we minimize the number of write back and fence instructions and still have data structures that are correct? So let's move on to the question of correctness. A little bit of background first. Linearizability is the standard correctness criterion for concurrent data structures, and hopefully many or even most of the people listening to this talk today are familiar with it, but for those who aren't, the idea with linearizability is that we have an abstraction like a set or a queue or a priority queue that has well understood behavior, and we know what it's supposed to do if one thread uses it one operation at a time. But we want to understand what it means for it to be correct if implemented concurrently so that multiple threads can have operations active at the same time. Linearizability says that whatever history of execution we get, that is, whatever interleaving of calls and returns to operations provide multiple threads on the data structure, the overall behavior that we get, this sequence of invocations and responses to operations and all their arguments, is equivalent to some sequential execution where the operations would be performed one at a time. We have the same arguments and the same return values to the same, it's just that they're overlapping in time. That sequential execution that we're equivalent to has to be one that makes sense for the data structure. So, you know, if it's a queue, then the nth DQ operation should get the value that was put in by the nth NQ operation. That's the semantics of the object that we want. Second, we want the sequential execution that we're equivalent to match program order in every thread. So the operations performed by a particular thread appear to happen in order. And finally, we want so-called real-time order, so that if thread 1 performs an operation and it returns, and then thread 2 performs an operation and it returns, we're guaranteed that thread 1's operation happens before thread 2's operation. That's important because when thread 1 returns from its operation, it might tell thread 2 somehow that it had done so. So, you know, hey, thread 2, I just did this operation, and now thread 2 does its own operation. It has reason to expect that thread 1's operation happened first. That real-time order allows us to have a bunch of different concurrent data structures in the same program. If every individual data structure is linearizable, then the whole program is guaranteed to be linearizable. That's the so-called locality property for linearizable data structures. And all of that is traditional management of concurrent data structures. We need to talk about what to do to extend this to handle persistent data structures. There have been several definitions for correctness criteria proposed. The one that has become standard now and is being used by just about everybody working in the field is one that Joe Izraelovich, Hammurabi Mendez, and I proposed at a conference about 4 years ago. And this is something we call durable linearizability. We say that a history, that is a sequence of invocations and responses of operations on a concurrent data structure, this history is durably linearizable if, first of all, no thread survives a crash. After a crash, we get a new set of threads. We never try to reason about one thread across crashes. That simplifies many things. And then second, the history, if you just take the crashes out, pretend they didn't happen, that history is linearizable. Very straightforward definition. It's actually a simpler definition than several that were proposed previously in the literature, but it works very well for a failure model in which the whole system goes down as a single crash. Michal Friedman and her co-authors a couple years later noted that there's an equivalent definition for durable linearizability that is sometimes easier to reason about. They say that a history is durably linearizable, again, if it's well formed. Second, if every operation persists before it returns. And third, if the order of the persists matches the linearization order of the operations on the data structure. Of course, persistence is expensive. Doing it before returning slows down each operation a lot. And that means that anything that is durably linearizable is likely to be slow. We may be able to make it modestly slow instead of terribly slow, but we're basically doomed to have a write back and fence inside every durably linearizable operation. And that may be okay if you're doing an update to a database. But if you're trying to do, a push onto a stack, waiting 100 nanoseconds for the push to persist before returning to the calling thread is very unattractive. And so there's a buffered variant of durable linearizability that allows you to get higher performance. We say now that a history is buffered durably linearizable if you might lose some information on a crash, but what you get is still consistent. Or a little bit more specifically, if you think of the crashes as dividing your history into eras. So this is my program run along here to right in the picture. The vertical lines are crashes. And on each crash, I may lose some information. But I will insist that the whole execution of a crash is linearizable. Some consistent prefix of the execution prior to the first crash, concatenated execution between the first and second crash has to be linearizable. Some prefix of the first era plus some prefix of the second era plus the entire third era has to be linearizable, and so forth as our program executes across potentially multiple crashes. The buffering that you're allowed to do makes it possible to delay the write back and fence of an operation as long as you get that when it persists, it will do so in the right order. And if you can do that somehow, either in hardware or in software, you may dramatically reduce the latency of individual operations. So we'll talk more about certain data structures being buffered durably linearizable as we go along. Let's think now about techniques that could be used to ensure that a particular data structure is durably linearizable or perhaps buffered durably linearizable. And in order to understand this, we have to think a little bit about the memory model of the hardware. Most people are familiar with the notion of memory models, most people who write concurrent programs at least. Everybody knows what sequentiality is. It's what we all wish we had, but we don't because no current machines other than IBM's Z-series machines provide sequential consistency. That is, memory doesn't really do everything in one global total order. The memory model of a particular machine tells you which instructions are guaranteed to be ordered, and more importantly, which writes may be seen by a given read in a program. So if I do a load instruction, what values written by store instructions am I allowed to see as a result load? On an x86 machine and on SPARC machines made by Oracle, the memory model is something called total store order. That says there is a global order on certain special instructions, the synchronizing instructions, including fences like the M fence and S fence, and atomic instructions like compare and swap. But ordinary instructions, the ones that aren't synchronizing instructions, are more loosely ordered. Specifically, if my thread performs a write and then a read, those two instructions are not guaranteed to occur in the order I did from other threads' perspectives. Because when I do the write, the hardware wants to execute the write slowly in the background and let it work its way through the cache system while I go ahead and do the read. If I read my own write, I'll pull it out of my processor's store buffer, but it's possible that I may see something that was in my read. I may see something that was written by somebody else after my own write, but I may not see that because my write hasn't reached anybody else yet. That's hard to wrap your brain around if it's the first time that you've heard it. So the thing to keep in mind on an x86 is that if I do two reads, or if I do two writes, or if I do a read followed by a write, the hardware does those in order. But if I do a write followed by a read, the hardware may do them out of order. And I have to figure out what that has to do with persistence. In particular, I have to extend the memory model of the hardware to explain the ordering of the persistence instructions. That paper at DISC back in 2016 that introduced linearizability also introduced a general model for memory behavior distance. And in that general model, there are write back and fence instructions, and there's also a sync instruction that's used prior to I/O but can be ignored for the purposes of this talk. The model in the paper subsumes the behavior of the x86 and multiple other currently available machines. Simplifying a bit because I don't have the time to go into the real details here, all of the persistence instructions are guaranteed to be ordered with respect to subsequent atomic operations and locks and fences. So if I write something back, or if I store something, of course, and then I do a fence instruction or a synchronization instruction, it's guaranteed that those will happen in order. Similarly, as has always been the case, if I do an atomic instruction or a fence and then a load, those are guaranteed to occur in order. And now, if I do a load in my program, and we think about all the instructions executed anywhere in the machine, my load is allowed to see the most recent store on some backward chain of orderings. It's also allowed to see a store that has no relationship to the read. There is a chain of ordering between the two. So those are said to be a data race, and the hardware will allow the load to return the values stored in a data race. And on a persistent memory, it could be the value that persisted most recently before the crash, if there hasn't been an ordered intervening write. Maybe I should pause for a minute before moving on. Any questions I should field here?
So we have a nice question.
Okay.
So, is it possible to somehow install enough batteries into the machine so that it is guaranteed, even in case of a crash, all the memory which is in the CPU caches now is written to the persistent memory?
Yes, that is possible. There are two ways to make it possible. One is to just automatically insist that the hardware write things back in the order that the writes happened in the execution. That dramatically constrains cache is allowed to do. Generally, anybody who's thought about this has decided that they'll do write through from their caches rather than write back. That means the caches can still be useful, but there'll be a lot more memory traffic, and the memory traffic will have to be carefully ordered. You can design a machine that way. It will be more expensive and lower performance than the machines we have. The other option is to make the caches persistent so that whatever is in the cache will be preserved on power failure or other kinds of crashes. And Intel is actively pursuing that option. There's a good chance that at some point in the not too distant future, caches will be guaranteed to be persistent, either because they're made out of STT-MRAM or because they have on-chip capacitors that are large enough to write back the entire cache contents on a crash. we'll see how that works out. If we're lucky, Intel will have that done before terribly long, and then much of what is complicated for system programmers in my talk today will get simpler.
Yes, I'm right that. Sorry, I'm right that in this case we can use the same hardware memory models as we use now. So we don't need to care about special instructions if we're sure that all the memory is persistent anyway.
Yep, that would take care of it. So these extensions that I've just described are needed for current machines in which the caches are volatile.
Okay.
And we have another question. Some our listeners asks to clarify the well-formedness on the linearizability with no thread survives a crash issue. So could you please explain again to make them understand it correctly?
I'm not 100% sure I understand the question. You're just looking for for me to restate linearizability and durable linearizability?
Yes, the point, what's meaning the well-formedness and that no thread survives a crash? What does it mean?
Yeah. The goal in this talk is for a data structure to survive a crash so that new programs can use it after the crash. So if, for instance, I have a key value store and I'm keeping it in Optane and I crash, when I bring the machine back up, I will have a usable key value store, and it will contain either exactly what it contained right before the crash or what it contained shortly before the crash in the buffered case. And I can go forward. I am not trying to recover the programs that were using the key value store before the crash. And in some previous papers, people had tried to imagine bringing back the threads. And then you had to ask, suppose my thread was in the middle of an operation when the crash happened, and your thread was in the middle of an operation too. What do we know ordering of those two operations that cross the crash? And that introduces all sorts of complexity that that is not helpful and just gets in the way. So we assume here that when you have a crash, all the threads go away, and the history after the crash has operations performed by new threads.
So your model suppose that we have some kind of atomic crashes, which stops just all instructions immediately.
Well, all instructions, yes, but there will definitely be operations that are partially completed when the crash happens. That's the failure atomicity problem. We have to do something to make sure that an operation that was halfway completed at the crash is either finished after the crash or is completely undone. And that's a challenge that we'll see in multiple data structures and systems later on in the class.
I guess, for example, if you have a lock, a fair lock, and you want to guarantee that all the requests that should wait for a lock are processed in the queue-like order, then after the crash. So if it is atomic, like Dmitry just suggested, you would want to keep this ordering, but in your formalism you don't care because you have a crash. It's bad anyway, so you don't care about fairness. It's more or less about fairness.
If there were 6 threads waiting for a lock, the threads are gone. They're not executing anymore. The one thread that had the lock needs to either finish its operation or have its operation rolled back so that the data structure is consistent.
Yes, and the other threads should restart the operations, and they should start acquiring the lock from the beginning so that the ordering can change.
Yeah, think again of the key value store. Suppose I'm running this on a machine in a data data, and I have a key value store that represents items in the database that my company sells. And somebody is in the process of changing the price and the availability on a particular item in my inventory, and the machine goes down. When the machine comes back up again, that thread that was making the change is not, it's gone. And either the change happened or it didn't happen. And now my database of things that my company sells is usable. Start new servers and start my, my e-commerce pipeline back and start talking to customers over the internet again, and I can use my inventory. And it may or may not reflect the change that was in process at the time of the crash.
Okay.
But I have a whole new suite of process running on the website with the old database.
I guess now we all understand, and I would suggest continuing.
Okay, cool.
Thank you.
So one more thing that was in that disk paper from 2016 is a mechanical transform for taking correct concurrent code and making it persistent. So for simplicity, let's assume for the moment that I have a non-blocking data structure. If I replace every store release, and I should say the paper was written on the assumption of release consistency, which is a more general model similar to what IBM Power and ARM processors have, but it subsumes what happens on the x86. If I replace every store instruction with a store and a write back, I replace every synchronizing store with a fence, a store, and a write back. I replace every synchronizing load with itself, a write back, and a fence. And I make similar changes to atomic operations like compare and swap and leave loads alone. If I make all of those changes at the instruction level in my program, then I am guaranteed that my non-blocking data structure is now durably linearizable. And the proof of that is fairly straightforward with one tricky part. Notice that whenever I write something, I am persisting it. Not necessarily fencing it, but I'm telling the cache to write it back now. And whenever I synchronize with another thread, I'm performing a fence to make sure that all of my previous writebacks have happened. When I do a load that synchronizes, I am writing back the synchronization variable itself just in case the thread that written it back yet. And I'm fencing to make sure that everything that has happened before my load has persisted, not only in my own thread, but in all the threads that are known to be ordered before me. I do a similar operation on a CAS, but the trick is that here I'm persisting the synchronization variable that somebody else wrote. So when there's a dependence from one thread to another, thread 1 writes something and thread 2 reads it. Thread 2 is obligated to persist what it read. And that's the case we saw earlier, that cross-thread handling of persistence. And it's built into the mechanical transform right there on the third line, the one that says this is tricky. So if your original code, data-free and linearizable, the transformed code is durably linearizable. And if your original code was non-blocking, you don't have to do anything in recovery in order to keep using your data structure, because in a non-block data structure, every possible memory contents is usable. However, this doesn't give you failure. If you have a lock-based program, when you wake up after a crash, you will have the correct state of memory for a halfway completed operation that holds some locks, but you won't know how to finish the operation or to roll it back unless you do something else that the mechanical transform does not give you. So this is not yet a recipe for failure atomicity. And second, this is slow because it has lots of writebacks and lots of fences. So it proves that we can, in general, automate the process of persisting data structures, but it does not give us a way to produce high performance data structures. And we're going to want to figure that out. All right, so let's talk about the failure atomicity problem for a minute. We borrow ideas that have been known for a long time in the database and file system community. The two traditional mechanisms for logging to ensure failure atomicity are so-called undo and redo logging. The idea in undo logging is while I'm performing a complicated operation that needs to be failure atomic, each time I update an individual variable, I will add an entry to my log that says what the previous value was. And now if I get interrupted halfway through, I may have just put something into the log, and I may or may not have changed the thing whose original value I logged. But in recovery, I can start at the end of the log and go backwards and put back all the original values. The very last thing in the undo log, I may or may not need to undo it, but it's harmless to undo it if the update didn't actually happen before the log, before the crash. So with undo logging, I am going to roll back a partially completed operation. Redo logging is the opposite. As I go along, I don't actually change the real data. I log the new values that I want to use to change the real data. And when I have figured out everything that I want to do, then I mark the log as completed. And then, assuming we do not crash, I go ahead and make the real changes to the data. Now, if a crash happens partway through the operation, then I haven't actually changed any real data, so my operation hasn't happened at all, and that's fine. If I completed the log and I had started making the real updates when the crash happened, now the recovery process can look at the log and it knows everything I was supposed to do to make my operation finish, because the log says that the log record itself was complete. So the recovery process can roll my operation forward and do its rights. Some of those may be redundant. Maybe they actually happened before the crash and persisted, but that's okay. It's harmless to do them again. So undo logging rolls incomplete operations back. Redo logging rolls incomplete operations forward and completes them. The main disadvantage of undo logging is every time I add one word of information to the log, I have to write it back and fence it before I can change the real data, because the log is needed in order to fix my change to real data on a crash. So with undo logging, I get lots and lots of persist operations, and it's slow. The problem with redo logging is that as I go along, whenever I read some real data, I have to worry about the possibility that I might have already decided to write it. So I have to look at the redo log as I go along in order to see my own rights. That complicates the software, but it doesn't add nearly as much overhead as undo logging. So redo logging tends to be a little bit more complicated, but higher performance. There's a third option that was introduced by Joe Izraelovich at ASPLOS in 2018 called just do logging, that I'll talk about a little bit more detail later on. It doesn't roll forward or roll back. Instead, it sort of recovers the failed threads. Not completely, just enough to execute the rest of operations. We'll talk more about that in a bit. And then finally, there's a notion of so-called periodic persistence that says instead of incrementally logging things as I go along, I will do occasional checkpoints of everything. So I could either have two separate copies, and I do my work on one in DRAM, say, and every once in a while I copy everything from DRAM into non-volatile memory and then flip one bit that says use the new version instead of the old. Or I could have a data structure that keeps track of its own history of all of its changes, and in recovery, arrange to ignore the most recent updates. And I'll talk about both of these options more as we go along. That was one of the two things the mechanical transform didn't give us. It didn't give us failure atomicity. The other thing the mechanical transform doesn't give us is a way to reduce the number of fences. So we need to think about that. Notice that writebacks themselves are not very expensive. They're a little bit expensive, but they're not bad because they pipeline. I can do a whole sequence of writebacks in a row, and I wait just a little bit of time between them, and then they pipeline their way to memory, and waiting for them at the end is what's slow. So it's desirable to design our algorithms to perform multiple writes between fences. And we'll see over and over again as we look at concrete examples that that's a standard thing people do. They try to avoid fencing each individual write, but instead do lots of writes that are permitted to persist in different orders, as long as you get them all done eventually. So ways to go about this include, as I mentioned a moment ago, preferring redo over undo logging. If we do redo logging, then we can avoid the need to fence every individual addition to the log. Second idiom is when we initialize an object before it's visible to other threads. We've just allocated the memory and now we're filling in its initial values. We can fill in all of those values. We can write back all the lines, the cache lines that comprise this object, and then fence higher initialization. And we know that's safe because nobody but our one thread can see the object. A third idiom is to notice that in some cases, the recovery procedure can figure things out that may be a little slow to figure out during recovery, but we don't expect to recover often, right? Crashes don't happen very often. We can avoid persisting information entirely if during recovery we can rebuild it. And the extreme example, which we'll see a more detailed case of later on in the class, is a set abstraction. If I have a large collection of items and all I have is the items and no index, I'm still okay, because in recovery, I can look through all the items and rebuild my index. So imagine a red-black tree or a hash table or a skip list that's used as an index into a set. The leaves of the data structure are the actual items, and they're really the only thing we need to persist, because during recovery, we can rebuild the tree or the hash table or the skip list, as long as crashes are fairly rare and we're willing to spend the time necessary to rebuild the index. And finally, we can consider buffered durably linearizable data structures instead of strictly linearizable ones, so that we get less overhead during normal operation at the expense of potentially losing a little bit of information at a crash. And every one of these strategies requires that we have some way of proving things correct. So let's consider correctness proofs for a minute. When people talk about linearizability, it is common, though not universal, to describe proofs in terms of so-called linearization points. Those are the instructions at which an operation appears to happen. And the linearization point has to be someplace between the call and the return. So the standard proof technique for a non-blocking data structure is to say, prior to this particular instruction, everybody can tell that the operation has not happened. And after this special instruction, everybody can tell that the operation has happened. So everything that I did before was harmless preparation, and everything I do afterwards is harmless cleanup. And the magic instruction is the point at which it appears to happen. That needs to be between the call and return in order to get this locality property for non-blocking data structures. And proofs in papers very commonly leverage this notion of linearization. Often, but not always, the linearization point ends up being an instruction that you know statically in the code. You can look and say, this compare and swap instruction is the place at which the code linearizes. It's important to understand that's not always the case. There are some complicated, even actually some simple non-blocking algorithms where you can't look at the static code on paper and say what the linearization points are. They're determined dynamically at runtime. There are even more complicated cases in which when an operation returns, you know that it has linearized, but you don't actually know what instruction inside caused the linearization, and you won't know until other threads do some other things. All of that aside, the notion of a linearization point is very useful for proofs and can be extended to persistence. So think of the notion of a persist point. This is a possible strategy for proving that algorithms are correct. It's not necessary, but it's sufficient. We say that an implementation is durably linearizable if somewhere between its linearization point and its return, all the stores that are needed in order to capture the operation and realize after a crash that it has happened have indeed been written back and fenced. So there's a persist point after you linearize and before you return, when everything that is necessary for recovery has been written back and fenced. That's the first property. Second is that whenever two operations overlap in time, basically their linearization order and persist order is the same. That means either that M1 comes first, so it persists before M2 linearizes, or else M2 comes first and it persists before M1 linearizes. And if you can prove those two properties for your algorithm, then you'll know that it's durably linearizable. Keep in mind that in order to write for which you will be able to prove this, you're almost guaranteed to need to do what the mechanical transform did and what my early example showed you need to do, and that is persist things you read if you depend on them. You can think of that as a kind of helping in concurrent algorithms, where somebody has linearized an operation and they're going to persist it. But because it is linearized, you can see it. And you don't know whether they have finished persisting it yet. So you have to help and make sure that it is persisted before you act on what they did and do something of your own that might accidentally persist and live after a crash. So that's the general strategy for proving that a data structure is durably linearizable. This is a natural place to stop for questions and I think perhaps to take the break. We're about 5 minutes before the scheduled time for the break, so if there's a couple of questions, I'd be happy to field them, and then we can head off for our little bit of space before the second half of the class.
Well, actually, I have a question from myself.
Sure.
Am I right what if we thinking about some kind of logging like redo or undo, we have to use at least two fences to NVMe because we need to flush every body of the record. But when we separately must flash the mark what it's completed, because on our case
Yes.
we will get sporadically corrupted record.
You're absolutely right. You can prove that for a durably linearizable operation based on logging, you have to have at least two fences. You have to do redo logging, write the entire log, and persist the log before you start making the updates. And when you finish the real updates, you have to persist them before you return.
And the second point, that our low-level mechanism don't have some kind of CAS instructions would connect it to persistence. So we need some actually helping on the usual algorithm to ensure what we have some kind of atomicity or separating our flashing.
I'm not sure I understand the question.
You showed the operations that ensure the flashing, and nothing of it has some kind of compare and exchange behavior. So we can't just compare and persist in the atomic way.
Right. None of the atomic instructions are simultaneously modifying memory visible to other threads and persisting it. So if the instruction set gave us a, say, persistent CAS, so that I could do a compare and swap that became visible to other threads at the exact same instant that it persisted, that would be very useful. But the hardware doesn't give me that.
Okay.
So I have one more question. Probably it will be covered later in the second slot. But when you build a durable linearizable data structure, you need to help to persist the memory, persist the updates. And I'm just thinking whether it is cheaper to maintain some flag on whether the update is already persisted in order to reduce the number of flashes.
Yep. There's a technique that that's been noticed, I think, by several people, but it was formalized by David et al., and I will mention it in the second half of the class, that works on a very clever idea. People in systems are familiar with techniques that mark pointers. Every pointer points to something that is an aligned location. So the couple of low bits pointer could be used for other things. We'll use one bit to indicate that this pointer has not been persisted yet. So now when I create a pointer to something and I haven't persisted this pointer yet, so it's not safe to dereference it and act on the things that it points at, I'll be able to tell because the pointer will have a bit set. I still have to help, but now I help, I'll clear the bit, and that means if thread A writes a pointer and 20 other threads read it, only one of them actually has to persist it. The other 19 can notice that the bit has been changed and avoid the expense, which is a nice idea.
Cool. So I guess we have not many time now. So I would like to thank you for a really great introduction to the non-volatile memory, and we are looking forward to the second slot about the algorithms and allocation problems.
Great. I'll see you all shortly. During the break, I skimmed through the chat of questions, and I saw several around the failure model, and I think I should say a little bit more about before proceeding. I've been talking mostly about power failures, and the durable linearizability paper assumes failures like power failure or loss of some critical feature on the backplane or the memory interconnect that basically makes the system unusable. That's not, of course, the only kind of failure. The most common failures are individual processes going down because they seg fault or divide by zero or something. That is not, for the most part, what durable linearizability talks about, but it's something that can be accommodated with an extension to the model. And I was going to plan to hint at that towards the end of this class. The crucial thing is that we are not expecting a process that dies to be brought back and to be allowed to continue after it had died. So we can extend the failure model where all threads die and new threads are created after the crash to a more sophisticated failure model where some threads die and are perhaps replaced by new threads. Other threads continue to execute the problem, but we still don't want to deal with the case of a thread dies and we create a new thread that pretends to be the old one and tries to pick up in the middle of an operation where the old one left off. We're not trying to accommodate that in the failure model because it isn't needed in practice, and it introduces complexity into the formalism and the algorithms that just confuses us. Also, there were a couple of questions about frequency at which crashes or other failures are expected, and the answer is not often. We have uptimes of weeks or months on most machines, so it's not like we're trying to optimize performance here. What we're trying to do is ensure that when a crash happens, it doesn't destroy our long-lived data. Imagine if your file system became unusable after a crash. We couldn't tolerate that. That's why we put so much effort into creating file systems that survive crashes and are usable by new processes after the machine comes back up. We need the exact same thing if we're going to take information that was in files historically and put it into main memory and keep it across crashes. So we're talking about persistent data, long-lived data that's traditionally in files. We want to keep it in memory instead. We need the same guarantee that we have for the file system. That is, that the data structure itself maintains its integrity and has a consistent state after we come back up. That said, I'd like to move into a discussion of particular data structures and techniques that were used to create those data structures that can then be generalized and used to create purpose systems for building more data structures and for combining structures into larger programs. The list of individual data structures designed for persistent memory is long and growing. I have put just a few things onto this slide. And, I encourage you to go off and read all these papers. They're generally interesting papers, and the list gets longer all the time, as you can see from the number of these that I've included that are in the last 2 years. There is no way in the remaining hour and a half of this class that I'm going to be able to describe how all of these data structures work. What I'm going to try to do instead is to pull out ideas from the algorithms in these papers that are generalizable, that work across a wide variety of data structures and that can be built into more general purpose systems. So the next several slides will cover ideas that come out of these papers and others like them. One idea is that non-blocking structures are particularly nice for persistent memory because by definition, any reachable state of a non-blocking structure is consistent. Prior to the linearizing instruction, the operation has not happened. After the linearizing instruction, the operation has happened, and all other threads, if they look at the state of the data structure, will agree on whether the operation has happened or not. The nice thing about that is that if you recover a non-blocking structure and it's consistent, then the recovery process is empty. There's nothing you have to do to it to keep using it. If you have a lock-based structure, by comparison, and some thread was halfway through an operation under the protection of a lock, then you need extra machinery for failure atomicity in order to roll the operation forward or back. Non-blocking structures avoid the need for roll forward and roll back and the need for logging on a crash. Second idea, transactional memory in hardware is a really nice tool for writing concurrent data structures, particularly non-blocking concurrent data structures, because it lets you modify multiple locations in memory atomically with a single instruction, the hardware transaction commit instruction. On most modern machines, of course, the transactional memory is just best effort, meaning that you'll have to have some alternative code path that's maybe slower that you can fall back to if the transactional memory doesn't work. But as long as it does work, you get an atomic change to multiple locations. The extension of that to persistence is not completely trivial, because if I modify several cache lines in a hardware transaction, and then I commit the hardware transaction, all other currently running threads will see the changes to all of my cache lines simultaneously, which is great. But the cache will still write those cache lines back to memory one at a time in arbitrary order. So I don't get atomicity of the hardware transaction in persist unless I'm very careful. And one thing I can do is to say, transactional memory will be used in this special purpose persistent algorithm to change an entire cache line. So a 64-byte cache line, I may make multiple changes to that line. As long as all the changes are in one line, when I commit the hardware transaction, I can then persist it with a single write back. So there's several algorithms out there that have redesigned their data structure so that the multi-word atomic updates are all contained in a single cache line, and that allows them to fairly easy persistence afterwards. A third idea, which I mentioned before we took our break, is by David et al. From the Usenix ATC conference in 2018. This is the link and persist idea, which I've already described. You mark each pointer, and then when you read the pointer, you know that you have to persist it if the mark is still set. And after you persist it, you can turn the mark off. Several threads that read the pointer at about the same time may all do a write back instruction, but one of them will succeed at the cas that turns the bit off, and any future thread that comes along will know that it doesn't have to persist the pointer and pay fence of the write back and fence. It'll also introduce a notion they call link caching, which is kind of an alternative to the link and persist. Instead of tagging pointers, they create a high performance concurrent set in transient memory that hold the addresses of the pointers that need to be persisted. And the idea is every time I create a persistent pointer, a pointer that will eventually need to be persisted, I put it into the set. And anytime anybody reads a pointer that's in the set, they go ahead and write back everything in the set and issue a single fence. It's basically the same idea as link and persist, except that I'm doing set insertions and lookups instead of tagging low bits. And crucially, I can do a single fence to protect a whole bunch of writebacks. When I need to write back a pointer, I'll also write back any other pointers that anybody else needs written back sometime soon and use one fence to persist them all. That's the first set of interesting ideas emerging from some of those algorithms on the previous slide. Second set, don't persist metadata that can be reconstructed. Again, I mentioned this before the break. If I have information that I'm using during normal execution for the sake of performance, like an index was set, so that in log time or maybe expected constant time, I can discover where something is in the set or not, that's redundant information. Just knowing the leaves of a tree or the contents of the chains of a hash table or the bottom level of a skip list is enough to tell you what's at. It isn't enough to look things up fast, but we can rebuild the index after a crash. So sometimes we'll just say, this data is written, it's here for the sake of performance, not correctness, so we don't have to persist it. Second idea on this slide, don't persist things that help you figure out what to do, but aren't necessary in order to verify that you're doing the right thing. This is an idea that is very similar to one found in transactional memory systems. many concurrent data structures have operations consisting of a search phase followed by an operation phase. So imagine in this picture here, I've got a linked list that's arbitrarily long, and it represents a set, and maybe it's kept in sorted order, as in the Harrison-Michael classic non-blocking linked list. So my algorithm to do an insertion is going to search down this list, starting at A and all the way to somewhere where it discovers, the place where I want to insert. I need to change one pointer to insert this node Y, and I'll be doing that with a CAS. I had this rule that said, whenever I depend on something that I read, I have to make sure it persists. This is the exception to the rule. Because once I get to this node X, and I'm looking at its next pointer, which points at Z, and I want to insert Y, which belongs between X and Z, I know I'm in the right place. And the fact that I went through A, B, C, D, E, and F to get there doesn't matter anymore. So if somebody has changed these early nodes in the list, I don't care. I know I'm still in the right place. And several algorithms used this idea. It was sort of formalized and written down by Michael Friedman and her co-authors at PLDI just last month. The idea being that during the search phase of an algorithm, you don't have to persist what you read as long as you can verify once you get to the right place that you are indeed in the right place. Third of interesting ideas that emerge from the algorithms in the literature is to leverage data structures that have long been studied in the functional programming community. And here I probably should have inserted a picture on my slide. If you imagine a search tree, for instance, and you want to make a change to the search tree and include some rebalancing. We all know that most of the tree remains the same as it was. The most work you do during a rebalancing operation changes a logarithmic number of nodes in the tree, and the bulk of the tree remains the same. In particular, worst case, a rotation or set of rotations to rebalance a tree creates a new spine from the root down to some particular leaf. I could allocate new nodes for that spine, a logarithmic number of nodes case, and their pointers, their child pointers, would point to pre-existing parts of the tree. If I do this, then I can move a pointer from the root, the old root, to the new root with a single CAS. And this is an old idea in concurrent algorithms. In the functional programming community, where you ever have side effects, right? You don't modify things, you just create new versions. The old versions may still be needed. So for complicated data structures, it's very common to keep the old root. So if I say rebalance a tree, I have the old root, I have the new root. Somebody else who comes along and does another rebalancing has yet another root, and I have all the old roots in a list. I do that in functional programming so that the old values of the tree, which are different variables in different contexts in the program, can still be used. And they simply share a lot of data, and the time to create a new tree is logarithmic instead of linear. In persistent programming, I have the possibility of keeping all the old versions, knowing that the newest version, or maybe the newest 2 versions, are still being worked on. So they may not be consistent yet, but the old versions are okay. And now after a crash, I might just throw away the new versions. That will give me buffered durable linearizability rather than strict durable linearizability, but it leverages this existing literature of history preserving data structures in a really nice way and minimizes the number of write back and fence operations that I have to do when creating a new version of my tree. The idea has been generalized very nicely by Herlihy et al. From Wisconsin at ASPLOS this year. They have a library they call MOD, minimally ordered data structures, I think is what it stands for. They basically took about 6 different data structures from the literature that are all history preserving and showed how to use them to build persistent abstractions. It's a nice paper and I recommend it. One concrete example of the history preserving data structure, and a relatively early one, is work that was done by a couple of students, Faisal Nawab and Joe Zrelovich at AP Labs back in 2016 or so. It was published at DISC in 2017. And it's a concrete data structure, a hash map, that actually maintains the history in each individual bucket of the hash table. And I thought I would describe this particular data structure because it's an interesting illustration of the history preservation. On the right in this figure, you see the header for a hash bucket. So each bucket of the hash table has this so-called status indicator, which is one word, which means you can update the entire status indicator with one CAS operation. Also in the header of the bucket are 3 pointers named pointer 0, pointer 1, and pointer 2. And their roles, what they're used for, change over time. The 3 early fields of the status indicator tell you what the roles are of the 3 pointers. The first field tells you which pointer is active, meaning it's the head of the list that is the elements in the bucket. The second pointer tells you which point in the list represents elements that have been committed but have not necessarily persisted yet, are being written back, but we don't know that they've made it all the way to memory. And the last pointer is the stuff of the bucket that is known to be persisted. Over time, we add things to the beginning of the bucket, but we never insert in the middle. So it's a prepend only unsorted list that you search when you land on a bucket by following the hash function. So the list is not expected to be long, but it has a prefix that's active and can't be counted on. Then it has a short section that is in the process of being written back and will soon be something you can count on, but on a crash, you still can't count on it. And then there's the last part that you can count on. After a crash, the DALI system ignores the prefix of every hash chain in every bucket, those first 2 pointers worth. And it can lazily update the pointers as it encounters buckets over time in the wake of a crash. The exact rules about how the roles of pointers change, you want to put something into the bucket, depend on what the global timestamp is and on what the local per bucket snapshot of that global time is, and are fairly complicated. There's a lookup table in the paper that describes all of this. The cool thing about this algorithm is that it's buffered durably linearizable. You lose information on a crash, and it leverages this history preserved data structure. So it can wait a significant amount of time, milliseconds, between changes to the global epoch number that allow it to persist larger suffixes of lists. Really carefully describing this algorithm so that everybody could understand it takes way more time than we have. So I encourage you to take a look at the paper, but I wanted to sort of highlight the idea. So those were several ideas emerging from the literature full of persistent data structures. What I want to turn to now is systems designed for building new data structures that leverage some of these ideas. Some of these systems are based on locks. Some give the programmer a transactional programming model, very much like software transactional memory. And some of them are yet more unusual, and we'll get to some of those special examples later. The classic example for locking goes back 6 years now. So this is some of the oldest work in the recent era of persistent memory. And it comes out of Hewlett-Packard Labs by Chakrabarty et al. From Uppsala. It's a Atlas. The idea in Atlas was to be able to take an existing program that uses locks for synchronization and highlight a data structure in that program that I would like to preserve across program runs and across crashes. We assume that the locks in the program are used to delimit critical sections that perform atomic updates to the data structure, and that locks may nest. They may also be hand-over-hand style staggered locks. So acquire A, acquire B, release B. Not necessarily properly nested, just as we know locks sometimes are not properly nested in real programs. But at some point, there's an outermost critical section. And that's what Atlas makes failure atomic. It says a maximal size region of code in which some lock is always being held, in which there is always at least one lock that is held, and the code region is of maximal size. We call that an outermost lock-based failure atomic section, or phase, which is kind of a nice pun in English with different spelling of phase. So we're going to make these phases failure atomic, and they're dictated by some existing software. The Atlas system does this with undo logging. They use undo logging rather than redo logging because, given that they're trying to support lock-based legacy programs, it turns out they sometimes have to roll back critical sections that have already completed. And we'll get to that in a second. They use compiler support to instrument the phases and to instrument individual accesses within the phases. So for the programmer, the burden is fairly light. The programmer has to identify the outermost locks. In principle, the compiler could figure those out, but they're determined by dynamic control flow, and it's much easier just to have the programmer delimit them. The programmer also delimits persistent data. So when you declare data and you want that data to be persistent, you have to put a special label on it. And then any accesses, reads or writes to that data inside a phase will be instrumented by the compiler. Finally, there's a special malloc and free implementation designed to work with Atlas, and the programmer is expected to use that for any dynamically allocated pieces of a persistent data structure. Okay, now the bit about having to roll back completed critical sections. In traditional lock-based programs, critical sections are not always isolated from one another. So imagine a nested critical section in which I have a block of code in which I hold lock A, and inside of it is a smaller block of code in which I hold lock B. Now, some other thread in my program needs to acquire lock B to do something that conflicts with my use of lock B, but they don't need lock A. So I've acquired lock A. While I'm holding lock A, I acquire lock B, and I do something, and I release lock B, and now this other thread acquires lock B, and it can perform some operation that runs concurrently with the rest of my phase while I'm still holding lock A. And worse, it may be the case that their operation aborts. And imagine that their operation had actually happened before my use of lock B. So I want to modify my example slightly. I should have drawn a picture. I start my critical section on lock A. While I'm holding lock A, they do something with lock B. Then I acquire the lock on B. And while I'm working on it, we have a crash. And my changes may have been seen by somebody else and acted on before the crash. We may have to roll back my operation. And as a result, we may have to roll back the operation that the other thread finished. So the short story is, inside a phase, because I don't have isolation, I can see a completed operation in another thread. And they can see things that I did. And if my outermost phase does not complete, and we have to roll my whole outermost phase back, we may be rolling back something that they depended on, and therefore we'll have to roll them back too. So we have to track the dependencies between phases based on who acquired which locks in which order. We have to track this across critical sections and be prepared to roll back completed critical sections on a crash. So Atlas tracks the relationships between critical sections, who acquired which lock in which order, in its undo log. The recovery process tries to figure out a frontier for happens before. The logs are local to every thread, and during recovery, the recovery process tries to find the latest point in every thread's log that represents a resistant cut across happens before. Once it has identified that latest possible consistent time boundary, then it takes every individual thread log and runs it backwards back to the boundary, undoing completed and uncompleted operations so that all of memory ends up reflecting the boundary that we found. Interestingly, that boundary is not necessarily one that actually occurred prior to the crash, but it's one that could have occurred prior to the crash in a program, in a run of this program with the same input. This is all assuming that the original program was data erase free. Final point worth mentioning with Atlas is that their special purpose allocator requires that the types in the program be such that it can do garbage collection after a crash in order to recover blocks that might otherwise leak. And I'll talk more about garbage collection later. So Atlas works, and it's kind of the reference point for lock-based general purpose persistent memory systems. Unfortunately, it's kind of slow, largely because it uses undo logging. And a lot of later systems have pointed out how much faster they're able to run than Atlas. One still lock-based is the Just Do system of Israelovich et al. From ASPLOS in 2016. And its goal was to outperform Atlas while still doing lock-based programs, ideally to provide a simpler system that wouldn't have to track the happens before relationship across critical sections. And in pursuit of that goal, they made a huge simplifying assumption, and that was that the caches were going to be non-volatile. So this is the one paper today that I'm planning to talk about that's designed for a world where the caches are non-volatile, and so we don't have to worry about inconsistency between cache contents and main memory contents. The goal is simply to get failure atomicity on lock-based critical sections, as in Atlas. So prior to every write, Just Do creates a tiny little log entry in the cache. So it's fast. And that log entry records the program counter and the live registers of the thread. So it gets reused the next time you do a write. So the entire log is just the amount of space required to hold the program counter and live registers of this thread. The log doesn't have to get larger for large atomic sections, for large phases, and the total space for logging across the entire program is the number of threads times the size register set. In the wake of a crash, Just Do assumes that you have access to the code of the original program, and the recovery process in Just Do executes the remainder of the current phase in every interrupted thread. It does not try to continue execution to the end of the program, just to the end of the phase. So it sort of rolls forward, but it rolls forward using the actual code rather than a traditional redo log, which records what you already decided after executing the code were the locations you wanted to modify. The overhead of Just Do, assuming that the caches are non-volatile, is less than an order of magnitude slowdown for failure atomic critical sections. So that's still a lot, right? Your atomic code itself slows down by 10x, but that's 3 times faster than Atlas. Unfortunately, JustDo does not do nearly as well if your caches are volatile. In that case, the slowdown for critical sections is 2 orders of magnitude, which is much more than anybody's willing to consider. So here's a system that tries to address that. Shortly after the JustDo paper was published, we were approached by a team at Georgia Tech that had been doing work on compilers, and in particular had been exploring the uses of idempotent regions in compilers. An idempotent code sequence is one that never reads its own writes, so that if you start it over again, it will do exactly the same thing it did the first time. So it can be interrupted and restarted an arbitrary number of times, and that will be harmless. Many programs have such idempotent regions. They're typically tens or even sometimes hundreds of instructions in length, and there are compiler optimizations that can be done to increase the average length of idempotent regions. And the cool idea that the Virginia Tech people had was that you can take the JustDo idea, and instead of logging at every store so that you can pick up from that particular store and doing it over is harmless, you can pick up at the beginning of an idempotent region. So the idea now is, in recovery, we will have for every thread a record of the last idempotent region they started. And we will start them all back up again at the beginnings of those most recent idempotent regions, which means we may redo tens or even hundreds of instructions in each thread, but it's harmless because it's idempotent, and we execute them forward to the end of each phase. That way, the logging operations have to happen much less often than they do in JustDo. And you can consider doing this on a machine that has volatile caches, and the performance is actually pretty good, and it's a significant improvement over Atlas. The only real downside is that now you need a smart compiler to identify and exploit the idempotent regions. So those are the 3 papers I wanted to talk about that do locking in a general purpose way that works across data structures so that they can persist essentially arbitrary existing lock-based concurrent data structures. And this is the point at which I want to move on to transactional programming models, but this is a good place to pause for questions if people have them. Anybody?
I have a question. Is it possible to use one of these systems in practice right now? Or these are just theoretical works with the proof of concepts?
These are all research code. So Atlas is available on the open source repository someplace. I'd have to look up where it is. But if you read the ASPLOS paper, or if you read the JustDo or IDO papers that cite it, it'll have the URL in it, and you can download Atlas and use it. It's a little bit brittle. It's not too bad. It's several years old now. There are some difficulties in doing the build. When you try to config and make, you'll discover you have newer versions of things that it doesn't want, and it's a little complicated to get it running now, but it will run. Several of the transaction systems that I'm about to talk about are available. Some of them are more recent and a bit less brittle because they're more recent. The only one that's really production quality at this point is the one that's built into Intel's persistent memory development kit, which I'll be talking about a little bit later.
Okay, I see. And it's not log-based, right? The one by Intel.
I'm sorry, it's what?
And
sorry?
The system by Intel is not log-based, right?
The system by Intel is log-based for the most part. It's actually not one system. It's a whole library of tools. The transactions that it includes do logging.
I see.
Almost everybody who's trying to do failure atomicity for code that is not non-blocking to start with has to do logging of some sort in order to be able to roll for operations forward or roll them back. So let's move on to transactions. The earliest of the modern transaction systems for non-volatile memory is a system called mnemosiny, named after the Greek goddess of memory, published by Harris Volos and others at Asplas in 2011. It is a software transactional memory system for persistent memory. It's an extension to the tiny STM of Felber et al. That had been published a few years earlier in PPOP. So the programming model is speculative during crash-free operation. Transactions that are concurrent and that do not interfere with each other can execute concurrently, can execute physically in parallel. But if they touch the same memory locations, then one other or sometimes both will be forced to roll back and retry. So as in all software transactional memory systems, there's this notion of detecting a conflict, rolling back and retrying. The mnemosiny people used the early Intel software transactional memory compiler to instrument their code. They made a few changes to that compiler in order to insert their favorite instrumentation rather than the instrumentation that Intel was inserting for their McCarty system. Mnemosiny keeps per thread redo logs. It uses redo for performance so that it won't have to do a fence operation on every individual word added to the log. And it uses global timestamps inherited from TinySTM in order to figure out the order in which transactions should be said to commit. It uses that order during recovery in order to redo partially completed operations. So if there are several transactions that had completed but not committed before the crash, that is, they'd finished writing their redo log, had not finished putting the values from the redo log into the regular locations in memory, then mnemosiny will replay the redo logs of all of those threads in order to reach a consistent state. And one of the cool ideas, should probably mention, coming out of this is a so-called torn bit log, which is an idea that generalizes to other systems and allows you to minimize the number of persist operations required for a log entry. So if we look in the picture here, we have a log that's part of a circular buffer. That's what the wraparound down here means. The log space is being reused over time. And a complete log record has matching torn bits in all of its entries. So this first sort of medium gray log entry here that says log record on it, all the torn bits are 1, so it's valid. Next to it is a log record that is still being built. And the idea is every time you write a word, you include 1 bit in the word of the log record that tells you whether it was written in this phase of the use of the log or whether it's left over from the last time you went through the log. And you know that this time through the log, we're writing 1s in the torn bit. When we wrap around and use the log again, we'll write 0s to the torn bit instead. Time we have a record that is all 0s in a 1 phase, we know it's left over from the previous phase. And if it's all 0s in a 0 phase, we know it's a completed and valid record. All this means is I don't have to write a special entry to the log that says I'm done writing the log. Instead, recovery can look at what's in the log and say, are all the torn bits matching? And if they are, it uses them. It's not a huge, deep idea, but it's important for the performance of mnemosiny. And this ends up being kind of the baseline system against which all of the subsequent transactional systems for persistent memory have been compared. And there are a lot of them. This is not a complete list. This is some of the transactional models for persistent memory that have been published since mnemosity. Actually, NV heaps here was presented at the same conference as mnemosity in the same session, within 20 minutes of each other. Many of these are more recent, including some that are all the way up to this year, one of which comes out of Rochester and is currently submitted to a conference. There are way too many details in these to go over them here, just as there were too many details to go over the individual data structures earlier. But I want to highlight a few key ideas that come out of these systems, several of which appear in more than one system. So, for instance, there's variety about the programming model, just as there is in non-persistent software transactional memory systems. Some of these have an object-based API, like NV heaps or like Pisces, where the programmer allocates objects and conflicts between transactions are detected at the granularity of objects, and new data is allocated and persisted at the granularity of objects. Other systems are word-based. That is, conflicts are detected at the granularity of individual words, and data can be modified in place. So I can have an existing structure that might have been an object in an object-based system, and I can change the field of it in place in a word-based system, and that may be more efficient than creating a new object that matches the old one everywhere except in the one field that I'm changing. So the advantage with object-based systems is that they're easier to make non-blocking, and it's easier to figure out where to put the metadata. It goes in the header of the object. You don't have to put it in a separate hash table, and you don't get false conflicts between things that happen to hash to the same metadata but are actually independent of each other. Some of these systems are library-based, so that it's just an API that you import from a library, and typically, those are kind of clunky to use. Others leverage the compiler to insert instrumentation so that you don't have to make so many library calls, or even extend the programming language, like, for instance, the object-based work of Cohen et al. From OOPSLA 2018, where there are language extensions that make things particularly easy for the programmer. Some of these systems are limited by the size of the DRAM because they use NVM as a copy of the DRAM. They use the DRAM as kind of the working copy, and then they checkpoint to the NVM. Disadvantage of that, of course, is that you only get persistent memory as large as you have DRAM. And part of the advantage of the persistent memory is that it's 8 times denser than DRAM. So your machine likely has much more non-volatile memory than it has DRAM. And if your system limits you to the amount of persistent data that will fit in DRAM, you're not going to be able to preserve most of your non-volatile memory across programs. But in return, you may get better performance. And there's trade-offs among all of these dimensions in which systems vary, and all of these papers are worth a read. And in the interest of getting other material before we run out of time, and I'm noticing I'm halfway through the seconds now, I'm going to avoid trying to go into great detail on it, with maybe one exception. There was a paper just this last month at PLDI, a system called Crafty, that I thought was particularly clever. And I wanted to mention it because it is the only persistent transactional system right now that makes really good use of hardware transactional memory. Prior to this paper, everyone had assumed that hardware transactional memory was incompatible with persistence because the write back and fence instructions cause a hardware transaction to abort. If you're in the middle of a hardware transaction and you do a cache line write back, your transaction aborts. You have to start over again. So how can you possibly do persistence if you can't persist inside a transaction? The realization that people had was that you can use the hardware transactions to create log entries in a really clever way. They actually do both undo and redo logging together in the same system. Here's the idea. First, I run a transaction that does what I want to do. So I want to make an update to my red-black tree, and it might involve rotating multiple levels of the tree, and it might touch lots of different cache lines. And I just write the code and do it. And when I get to the end of the transaction, I undo it before I commit. So as I went along, I run the transaction and I build an undo log. I don't persist the undo log in the transaction. I just build it in transient memory. And I go ahead and I make the changes to the real data inside the transaction. And of course, that's not visible to anybody else until I commit. So I'm running along. I can read my own writes easily. I don't have to do anything special the way I do with redo logging to look at the log to see my own writes, because I'm making the changes to the real data. And I'm building an undo log as I go along. When I get to the end of my transaction, before I commit, I traverse the undo log in reverse order, and I undo the real writes. So everything that I made as a change to real memory in order to read my own writes, I undo before I commit. And now I commit the hardware transaction. And all I have done effectively in that hardware transaction is create a redo log. So I built the undo log as I went along so that I could undo my real writes. And as I traverse the undo log at the end of my hardware transaction before committing, I undo the real writes and build a redo log. And this redo log is efficient because I don't have to read my own writes from it. I already did that from the real memory. And I also record a timestamp in the log so that I know how I'm ordered with respect to other transactions in the world, and I commit. So now I have committed a redo log, and I haven't made any changes to real memory yet. So that was the second step. Now the third step, I persist the undo log, and I can do that with one write back per cache line and a single. And then after I have persisted the undo log, I execute the redo log that I built. And I may actually use hardware transactional memory for that to make it especially fast, because remember, it's still concurrent with other threads and it might conflict with them. Finally, if that execution of the redo log succeeds, I'm done. If it fails because of a conflict with another thread, which I might detect by hardware transactional memory, or I might detect because of the timestamp that I saved, then I fall back and take a slow path that does everything at a higher cost. Finally, having having written the entries in the redo log, I issue persists writebacks for the modified data and one fence, and I mark the undo log as having been completed. Their performance for this system is pretty good. It does involve doing everything twice, but it involves very little in the way of fencing. So particularly for transactions that are independent of each other and can actually run physically parallel, they get much of the performance advantage of hardware transactional memory in a system that's compatible with persistence. So this was my favorite paper from PLDI this year. That's a good place to stop for just a moment before I talk about models other than locking and transactions. Questions?
And how efficient is this crafty, model?
It depends what you're comparing to. Okay, so if you're comparing to the original data structure with just the hardware transactional memory, then it's still several-fold slowdown. But if you're comparing to Mnemosiny or Atlas or most of the other transactional systems for persistence, it's better. So we're talking here about an interesting trade-off. Okay, we have a data structure that has a certain speed when in transient memory. And if we persist it, it slows down by a significant factor. And exactly how much, you can look at the examples in the paper. I actually don't remember exactly what the slowdowns were and which examples they were for, but it depends on what data structure you're doing. Let's say that it's somewhere in the 2 to 5 fold slowdown. That's a significant expense during your ongoing operation. On the other hand, it's taking the place of operations on files because you're manipulating data that you would otherwise be manipulating with file system reads and writes. And you're arranging to capture almost most recent version of the data on a crash. So if you're doing a file system, every once in a while you do file system writes in order to persist an intermediate state, but you have lots of complicated code to do that because you have to serialize your data structure, and you don't do it very often. Crafty is durably linearizable. It's not even buffered durably linearizable. So you lose almost nothing on a crash. In a file-based system, you lose everything since the last time you wrote to the file, and you avoid the complexity of the file system serialization and deserialization. So it's an interesting trade-off, and it's one that I think lots of people are going to be making over the next few years. Do we like the convenience and the small loss on crash of durable, persistent data structures, or do we like the lower overhead during non-crashing operation of transient data structures with occasional checkpointing to files? And I think every individual programming team is going to have to make that assessment.
By the way, is it possible to apply the same approach to make your data structure buffered durable linearizable? I mean, I guess you can use the same trick with the hardware transaction to
Yes.
to construct logs, but you don't need to persist every time. You can perform the transaction and create
Yes.
a log and a log entry and do this expensive logic once per several operations. Is that possible?
I think it should be possible to create a buffered version of Crafty. It's not immediately obvious to me exactly how it would work. I think there's some interesting questions that have to be addressed, because once you've finished the hardware transaction in Crafty, you don't know for sure that you're going to succeed. You've created a redo log, but until you try to execute the redo log and you look at the timestamps of conflicting transactions, you won't know for sure whether you are going to succeed or whether you have to roll back and retry. So in order to go forward in your program, to keep the next thing, you'd have to know that your redo can succeed. So you'd have to do some of the work of doing the redo. You could just avoid fencing the persists. And that might still be worth doing.
But
you need to keep track of the things that have to be fenced.
If you
I think that's an interesting subject to work.
If you don't need to persist, you can do both the redo log entry and the operation itself inside a single transaction. So that you don't have conflicts with other transactions.
Yeah, except that you have to persist the undo log and then the real data.
I see.
So it's a little tricky, but yes, I think that's a very good idea, and it's worth pursuing. Other questions on transactions before I go on to talk about a couple other things?
So no questions from my side, and I don't see questions in the chat.
Okay. There are other programming models for persistence that are worth knowing about. Perhaps the most interesting is one that has been championed by Terence Kelly, who was at HP for many years. He was one of the people involved in creating the Atlas system and the Makalu allocator that I'm going to talk about later, and several other things. Terence has been working as an independent since leaving HP a couple of years ago, and he has become an advocate for this programming model he calls failure atomic MSync. And there's a nice exposition of this model in the ACMQ Practitioner magazine from this last year. His idea is, let's keep the traditional notion of M mapping a file with a buffer cache interposed between DRAM and persistence. So it's a traditional M map where your updates are guaranteed not to persist until you do a sync. That's the normal model for MSync. But now we're going to persist them atomically when you do an MSync. So Terence proposed that we have DRAM buffering of non-volatile memory. We stage all of our updates in that DRAM copy, and then we say MSync, and everything that we've done since the last MSync gets atomically written into the persistent memory. This is a somewhat slower model than some of the others because you have to persist entire pages. There's nothing that's keeping track of which word inside a page has been modified. So if the virtual memory says that this page is dirty, then the whole page has to be copied from DRAM into non-volatile memory on an MSync. But it gives you a programming model that very conveniently captures what's atomic. Then also I've mentioned on this slide two recent systems that are more like the lock-based and transactional systems than failure atomic MSync is. So Pronto is work out of the very active non-volatile memory group at UC San Diego. Steve Swanson at San Diego has been one of the leaders of work on non-volatile memory for more than a decade. An amazing publication list coming out of his group, and Pronto is one of the recent projects led by his student Mamaripur and published at ASPLOS this year. They do periodic checkpointing plus logging of high-level operations, not of individual loads and stores. So the idea is we have a conceptually unbounded log that we will trim appropriately and garbage collect when we need to. What the log records is the high-level operations applied to our data structure. So instead of saying, here are 13 locations inside my red-black tree that need to be modified in order to perform my operation, instead you say, I'm inserting a 7. And that's what you log, the high-level name of the operation and its arguments. And then every once in a while, a background thread does sort of a consistent cut across the log different threads, because every thread has its own log and has a timestamp in the log that allows it to figure out how it's ordered with respect to other threads' logs. A background thread goes through, finds a consistent frontier across the logs of all the other threads and does a checkpoint of everything from DRAM into non-volatile memory. And then if you have a crash, you start from the most recent checkpoint and then replay the high-level operations using the code of the original program. So in this sense, it's a little bit like just do, in that you assume you have that code available during recovery in order to replay the most recent high-level operations in the log. It's a nice general purpose technique that can be applied to essentially arbitrary data structures, and they describe it being applied to several in their paper at ASPLOS. Then the montage system is one from my group, which is currently under development, and we're hoping to submit it to a conference in the next couple of months. And I'm not going to try to describe it here because it's not done yet, but I can hint at it a little bit. It is a buffered durably linearizable system and achieves significantly fewer than one fence per operation. And it builds on a special purpose non-volatile memory allocator called RALIC that I will be describing in a few more minutes later on in this class. So watch for montage later this year, led by my student. You know, I put the wrong name here. It's not, it's Went Outside. CAI should be the lead student name on the montage project. Then the last thing I should mention under general purpose systems before moving on to a couple of other topics in our remaining time is the Persistency Development Kit from Intel, which is the only real production quality suite of tools for working with persistent memory available at present. You can download it from Intel. It is a whole collection of different tools with multiple programming models, some of them quite low level, some of them quite high level, and various sort of utility programs. So it's a whole suite of tools available to programmers that you'll pick and choose from. Not all of these things would be used together in one program. Some of them even have kind of incompatible models with each other. You take what you want for your particular program. So they have several implementations of a log, for instance. They have failure atomic transactions, although interestingly, those transactions are not isolated. That is, they are not intended for synchronization among threads during normal operation. You have to do something else in your program to synchronize conflicting operations in different threads. But once you've synchronized, you can use the support in PMDK for failure atomicity. They have a memory allocator that I'll be saying a little bit more about in a minute. They have a key value store as an example of how to use the other tools. They have some tools for tests, which are pretty rudimentary at this point and very, very slow. That's another area that my group is working on. They have support for access to non-volatile memory across an InfiniBand or other data center network with remote direct memory access. So library routines that get at non-volatile memory on other machines and various other things. And it's not a completed system. They're still working on it. Intel keeps adding new tools to the suite. So if you're thinking about using Optane, you definitely need to get familiar with the tools that are inside PMDK, because almost everything else that I've talked about today has pieces inside that were drawn from PMDK. With all of that, I want to move on to memory allocation. I think we're doing okay on time. We've got 25 minutes left, and we'll use some of that for questions. So this is good. You can imagine persistent data structures that use statically allocated data only. You know, I have a collection of variables and maybe some big arrays that I've allocated, and all I do is modify locations in those. But that's not very interesting. Most of us want to build data structures that have dynamically created pieces, linked together pieces. So we need some sort of memory allocation and free. The most straightforward approach in order to integrate this with persistence is to include operations on the allocator inside the failure atomic operations of some larger system, whether it's transaction-based like Mnemosiny or whether it is lock-based like Atlas. You could just say an allocation is part of some bigger operation, and if I roll back the whole operation, I roll back the allocation too. If I roll forward the operation, then I'll roll forward any free operation that was part of it. But there's two problems with this approach. One is that if we're building a memory allocator is itself a complicated concurrent if it's being used by multiple threads. And there's, 40 years of research on how to make fast allocators. And they perform all sorts of optimizations, and optimizations for persistence are very much part of what you want an allocator to do. You would like to avoid unnecessary write back and fence operations inside the allocator. And if you're going to roll the reads and writes of the allocator into a system like Atlas or Mnemosiny, then you're going to pay overhead on every single read and write, even if a smart programmer could give you a persistent atomic allocate and free that did not have to do all of that overhead. So you give up a lot on potential handwritten optimizations for the allocator. Second, if you roll your allocator into larger operations, you get stronger semantics than you need. So if I have two transactions active concurrently and they're both allocating a block, and one of them gets a block with address 1, 2, 3, 4, and the other gets a block with address 5, 6, 7, 8, that's fine. And if we swap the blocks from the allocator, if the allocator gives them the transactions the other way around, we don't care. The actual address that you get back from malloc doesn't matter. All that matters is that it's a unique block that isn't being used by anybody else. So if we roll the allocator into one of these other systems, we will be guaranteeing that it allocates exactly the same blocks to exactly the same threads under all circumstances, which is stronger semantics than we need, and again, gives up on a possible optimization. And for these reasons, it's really desirable that the allocator be a separate abstraction. It should be its own persistent concurrent object, and you should combine it with another concurrent operation whenever you want to perform an operation that includes allocations. So you want to be able to have a failure atomic operation that works on, say, my red-black tree and on the allocator together. The problem with this approach is that even if the allocator is durably linearizable and the tree given an allocator is durably linearizable, I can have memory leaks because of the gaps between allocation and attachment to the data structure. So on the left in this slide, my cursor so I can gesture, trying anyway. Oh, there it is. Okay. On the left in this slide, I have a thread that has allocated a node, and it initializes it and then points a data structure pointer at a new node. So there's this period of time where I've created a new node that I want to add to the data structure, and I'm initializing it where it's no longer on the free list. I have it, but I haven't attached it to anything yet where it becomes visible to anybody else. So crash happens before I attach it to the data structure, as shown on the left here. I will leak that node. In recovery, it won't be on the free list, but it won't be attached to the data structure either. And similarly, over on the right here, if I have removed something from the data structure and I crash before I actually free it, then it won't be visible in the data structure and it won't be on the free list either. The immediate problem we have to deal with if we want to have an allocator that is a separate abstraction that can be used from inside operations on data structures that are supposed to be failure atomic. Perhaps the simplest solution is to change the interface allocator. And this is what PMDK does. The allocator that you get from Intel has this special malloc2 free-from interface. That's not exactly the name in the Intel library, but it's the name that's been used in the literature for this style of allocator. It's an allocator that gives you an atomic operation to allocate and attach a block. So in PMDK, I call the allocator and I give it the name of a constructor, the constructor, and the pointer in my data structure that I have point at the newly allocated object, and the allocator does all of that together as one atomic operation. In other words, malloc is not atomic. Malloc, initialize, and attach are atomic together as one operation provided by the allocator. And similarly, to deallocate on the right here in PMDK, I call a destructor and I provide as a parameter to the destructor the pointer in the data structure that is the last remaining pointer to this object. I have to destroy any other pointers myself beforehand. I have one remaining pointer to the object in my data structure, and I give that pointer to the free from operation, and it atomically breaks the pointer, changes it to null, and puts the object back on the free list. This works, and it avoids, you have a crash, there's never an object that's sitting in limbo between the allocator and the data structure. But the API is non-standard, which means if you're taking existing code and trying to create a persistent data structure based on this existing transient data structure, you have to change how you think about allocation, and you have to change all the calls to the allocator. It also requires that every operation on the allocator do write back and fence internally, which is expensive, as we know. If you're lucky and your allocator is grabbing something off of a thread local free, malloc should be just a small number of cycles. And adding 100 cycles to that for write back and fence is really unfortunate. So as an alternative, the group at HP, the same folks who did Atlas way back when, produced an allocator called Makalu. They published it at OOPSLA in 2016, and it uses the standard API, but instead of trying to make sure that every block is always attached to something, it uses garbage collection after a crash to find any blocks that have leaked. By default, Makalu uses the well-known BOEM allocator that does conservative garbage collection, even for languages like C and C++. So if you have Makalu in your persistent data structure, and by the way, Makalu is available for download. If you are using Makalu in your data structure, then during recovery, the recovery code will traverse the heap, and every long word aligned pointer, or every long word aligned datum, is assumed to perhaps be a pointer. And if it interpreted as an address happens to be the address at the beginning of a block, then that block is assumed to be allocated. It's the same technique that's been used for years for programs in C and C++. It has the possibility of leaking blocks, at least temporarily, if, say, you have a floating point number in your program somewhere whose bit pattern happens to look exactly like the address of one of the blocks in your heap. Makalu is still lock-based internally. It is doing a write back and fence operation inside every operation, so it remains fairly costly. As an alternative, our group published an allocator at ISMM this spring, just this last month, that expands on the garbage collection idea and much better performance. So it is a non-blocking allocator. It's based on the LR malloc allocator of Light and Rocha that was published at VECPAR back in 2018. It builds on their code. Their code is in turn based on Magid Mikhail's very famous allocator from PLDI about 15 years ago. Rallic, our allocator, does no write back or fence at all inside most operations. An occasional malloc or free will require a write back or fence, but only when it is allocating a new slab inside the allocator, getting it from the operating system. In addition, Rallic provides position-independent data. It exports a relative pointer abstraction, a smart pointer in C++, so that when you run a program over and over using the same heap, you don't have to guarantee that the heap is mapped to the same address in your program on every execution. And that's something you do have to do with Makalu and with PMDK's. Sorry, not with PMDK. With Makalu, you have to guarantee that the heap is mapped in the same place in every allocation. In PMDK, you use 128-bit pointers that combine a heap address and an offset. In Rallic, each pointer is represented by the signed offset to the target object inside this heap. So Rallic does not currently support pointers from one heap into a different heap. Everything is assumed to be a linked data structure inside the same heap. And if you look at the bits in a pointer, they tell you how many bytes away from the pointer the object is in memory. An odd thing about this is that two pointers to the same object residing in different places in memory won't actually have the same bit pattern to them because their distances to the object will be different. But the smart pointer code turns it into an ordinary pointer address on a load and puts it back as a store. And the overhead is one extra add or subtract instruction on every load or store of a pointer. And you get position independent data, which means we no longer have to worry about keeping the heap at the same address in every process. And there's an extension in RALIC to the conservative garbage collection. Basically, the programmer can provide functions that identify the pointers inside of blocks as an optional way to provide more refined garbage collection than you would get in Makalu. Performance experiments, which I could throw up if anybody is interested, but we'll leave out here in the interest of time, give performance for RALIC that is almost exactly the same as the famous J.E. Malik allocator that we compare to. J.E. Malik is transient only. It has nothing to do with persistence. So basically we're saying that the overhead of RALIC is very, very close to zero, giving you performance basically for free. And the key to that is to be non-blocking and to avoid persisting metadata. On a crash, RALIC simply traverses the heap, noting for every block what the internal pointers would be if it were pointers, tracing availability and garbage collecting the blocks that can't be found from the set of persistent roots and rebuilding the free lists. So all the free list metadata for different size classes is reconstructed after a crash in RALIC. That's a good place to pause again for questions. If there are any.
Well, actually, about memory allocation, I just thought that maybe some approaches that generally use it in allocators use it for languages like Java, maybe applied some here. Maybe some analog of approach in Shenandoah will be feasible because it supports moving objects and you could traverse allocation and metadata.
Yeah, there's a lot more that could be done with persistent allocators. Copying collectors in order to integrate with garbage collected languages could certainly be built on top of RALIC. If you have complete type information, as of course you would in Java or another managed language, then there's no worry about the conservative collection actually missing something. And because you know where all the pointers are, you can update them if you move blocks. So you could do a copy and collector, you could do generational collection. Basically, a garbage collection language like Java or Swift or C++ could be built on top of RALIC. The interface I just described is what it provides to C and C++.
So, okay, it's an extended point of research.
Yep. So let me mention a few more things. We got about 10 minutes left. I'm going to take 5 minutes of that to mention a few more topics, and then we'll move to questions. And I can stick around after the end for anybody who's able to stay for questions if you want. I mentioned before that the PMDK provides some tools for testing, and I did mention that they're slow. They are better than really crashing your machine. So here's the problem for testing. If I want to know whether my memory will be usable after a crash, I'm asking whether I will always have consistent data in memory when the caches do not write back. So how do I stop my caches from writing back? How do I look at the contents of memory without looking through the coherently cached cache system that normally stands between me and memory? Well, one way to do it is I have a machine that has Optane in it, and I run my program, and some point in the middle, I literally pull the power plug on my machine. And I let it crash, and the caches will not have time to write their contents back. I plug the machine back in again, I boot it up, and I look and see what's in Optane. and I look to see whether what's there is consistent. If it is, I say good, and I repeat. How many times do I have to repeat before I'm convinced that I have all the bugs out of my program? I don't know, but every one of these crashes probably takes me 20 minutes to reboot my machine, and it's really hard on the hardware. Machines do not like to crash. It's, you know, it's bad for the disks. It's bad for heat sensitive components that have fans. We don't really want to do that. We want some other way of looking at what's underneath the caches, even though the hardware is designed to prevent us from looking under the caches. We could imagine some sort of logic analyzer that plugs into the memory system underneath the caches, but nobody currently sells hardware that provides that. So the only real alternative is to instrument the program to capture the loads and stores, and to create sort of this separate memory trace stream that's been captured in software, and run it through some sort of cache emulator that allows us to infer what might be back in memory at any particular time, and then we can check that for consistency. PMDK provides a mechanism for this. It captures memory traces, and then there's a separate offline tool that will permute the loads and stores in that trace, and then you can use that to drive a simulation. But the permutation tool actually explores the entire state space. So it takes hours or days for trivial size programs and is unusable on real size programs. We are currently developing a tool called PMAT that we introduced at the Non-Volatile Memories Workshop this spring, and hope to submit to a conference again in the next couple of months, that intelligently samples from the state space in a way that's much more efficient than PMDK. There are lots of other research topics that people could pursue in this area of persistent memory. Certainly data structures that minimize their writes, both for performance, because writes are slower than reads in most non-volatile memory, and for endurance, because writes wear the memory out and reads don't. So data structures that will perform extra reads in order to avoid doing writes are worth exploring. Non-persistent systems that choose what to put in the large, slow memory are a very active topic of research in the operating systems community right now, because we expect to have data centers filled with these machines very soon, where you have maybe 8 times as much non-volatile memory as you have DRAM. You don't care that it's really just want to use it the way we've always used memory, but now you have a big slow memory and a small fast memory, and you have to decide what to put in each of those parts of the memory at a given point of time. And that's a very active OS research topic. Lots of work going on in file systems and databases that maintain the traditional API, so they're very usable by existing programs. You don't have to change your applications at all, but make very good use of non-volatile memory inside. Some of those use the non-volatile memory as an accelerator, like to hold the index so that your B tree is entirely in non-volatile memory instead of every level of the B tree requiring a disk seek. Others use the non-volatile memory itself as the file system and basically just give you a RAM file system in NVM. Both of those approaches are being pursued, again, both for file systems and for databases. Data center architects are considering how to build the hardware of new systems that have petabytes of byte addressable memory. So right now, I told you I have a machine in my lab that has 1.5 terabytes of NVM in it. That was the smallest amount we could buy. The machine wouldn't come from Dell configured with any smaller amount of NVM, but we could have gone up a lot. We could have put many, many terabytes of NVM in this machine. So now imagine a data center in which you have many petabytes of non-volatile memory. If you evenly divide that among all of your machines, then you'll have some machines that have lots of memory they aren't using. And you'll have other machines that wish they had more, because some of the machines in your data center are hosting databases and others are performing business logic that doesn't need very much memory. So it's possible that you could statically partition your memory and just have some big memory nodes and some small memory nodes, but that makes task allocation in the data center much more difficult. So an appealing alternative is to disaggregate the memory and design the hardware so that you can do cache fills across the data center network. And now you have sort of network attached memory, the same way we have in recent years gone to network attached storage. And instead of hooking disks up to individual blades, we hook them up to the network and you can access them from anywhere. Imagine now that you have this memory housed in special memory servers and you dynamically map different machines in the network. So there's a lot of active work in that area. Again, not making very much use of persistence, but making use of the size and low energy of non-volatile memory. Then one of my favorite topics and the thesis topic of one of my current students is imagining how we will manage persistent segments. So use the word segment to mean what used to be a file, where a file is in a file system and it's accessed with block-sized loads and stores, or reads and writes. A segment is now something that you can map into your address space, but it's persistent and you access it with loads and stores. One of the nice things about file systems is that we can peruse files independent of the programs that created them. Right? I can do an ls, I can do grep, I can cat or more a file and look at its insides. I can run it through OD and look at the data, even if it's not ASCII, and make sense of it. How do I do that for segments? Because they're pointer-rich data structures. Do I need type information embedded in them? Do I need binary to XML converters so that I can peruse them in a tool in my browser? What is the whole suite of tools, like all those Unix command line tools we have for files, that we need in order to deal with memory mappable segments instead? And I think that's a rich topic there. The last thing that I want to mention is an advertisement for my talk at Hydra tomorrow, which is about cross-application sharing. So in this picture, application 1 here may be making use of some shared memory currently labeled library A in the picture that's mapped into its address space. And when application 1 completes and terminates, the shared memory, library A, stays around and can be mapped in by some other program later. Application 2 may do something similar, but what about something that is actively shared at the same time by two different applications that don't trust each other? A key value store, for instance. If I have a key value store that contains stuff that I care about, and an application has the right to do inserts and removes in the key value store, it doesn't necessarily have the right to destroy the key value store and make it unusable by other applications. So somehow, I want to arrange to map shared memory, non-volatile shared memory, into an application in such a way that it can only be modified by a trusted library, so that when the application calls into the library, it gains access to the shared data that it didn't have before. And when it returns back into the application, it loses that access. And we'd like this to be fast. This way, we can safely share data between applications. And one of the really cool things about this from a concurrent data structures perspective is that now we have a failure model where individual processes can fail. Because I can have a shared abstraction that's being used by application 1 and application 2. And even if the libraries are trusted and bug-free, while application 2 is executing in one of its threads in the library, one of its other threads back up here in the purple section can divide by 0 or take a seg fault and crash the whole application. And now I have to be able to recover from this and continue execution in application 1 despite the fact that application 2 crashed, and without destroying the integrity of the shared data in the middle. And that's what my talk at Hydra is about tomorrow. And I will stop there and take additional questions. And I used up all my time, sorry.
I would probably ask a couple of more or less elementary questions. First of all, could you please clarify whether we can use standard atomic operations like compare set or fetching that on non-volatile memory?
Yes, but they work in the cache. Non-volatile memory is cached like any other memory, and if you perform an atomic operation, it atomically changes the cached data.
Okay.
So it's immediately visible atomically to every other thread that's actively running, but it is not necessarily back in main memory yet.
Okay, thank you. And the last question, because we're a bit late. For example, I want to try to implement one of the algorithms from the papers you mentioned, and I need to run it on some runtime system. Is there a runtime existing runtime system which I can use? I mean,
you mean if you want to experiment with this right now?
Yes.
The simplest way to get started is to download PMDK. That will give you handy library routines for interfacing with the DAX file system that's now part of Linux. So the latest releases of Linux have support for direct access to non-volatile memory, and Intel's libraries will give you the routines you want in order to look things up in the file system and map them into your address space, allocate objects using their allocator, create log entries using their log code. It's a very good way to get started.
Thank you. I hope that everybody who attended the lecture will try to play with it. So it's time to finish because the slot is already finished. We don't have any time, and we'll have a discussion zone tomorrow at 3 p.m. Moscow time.
So, right, and I'm looking forward to that. And my apologies for not leaving more time for questions here.
We have a lot of time tomorrow, so.
Yeah.
Thank you for the lecture. It was brilliant.
Thank you very much.
Thank you for all the help in making this possible online. I realize this has been an experiment for all of us, and my compliments to JUG for making it work.
Thank you.
Thank you.